My name's Aaron Levin. You can follow me on Twitter over here, and I think this photo will give you an idea for the kind of content you're going to get on there. I started this life as merely a mathematician. I studied these things called Banach lattices, which have nothing to do with programming and have never helped me understand any category theory. But like any sensible person, I got a job, and now I work on recommendations at Soundcloud. It's such a pleasure and a joy to work there. Most of my job is dealing with the horrible elements of data engineering, and then occasionally I get a little nugget of machine learning. So as much as I would love to talk at you for 35 minutes and make some weird jokes, I want to accomplish two things. One, I want to teach you about something called type-level DSLs. And number two, I want you to learn something and to walk away from this inspired to go and use these tools to build some amazing things. So to accomplish those two things, we're going to first talk about DSLs, make sure we're all on the same page, and then we're going to talk about type-level DSLs. Then we'll talk about some examples of where these are used in practice, and we're going to build together, like a beautiful family that we are, a type-level DSL for event processing, a problem that was modeled after something I experienced very intimately at my work. And then we're going to talk about the pains of being so pure in our design. So to begin, DSL. How many of you have heard of a DSL before? Okay, so for the people who didn't put up their hand, DSL is a domain-specific language. It's a programming language that was designed entirely for often a very narrow domain. And I hope each and every one of you have downloaded a web page, which means you've probably seen or encountered one of the most famous DSLs, HTML. I couldn't get a logo for HTML, so you got to suffer the HTML5 logo. It's a DSL that was designed to write how you mark up a web page to be consumed by a browser. Other DSLs, CSS is a really famous DSL. If you've ever had to compile some ancient C project, you've probably had to use GNU Make. And for the hardware engineers out there, I'm sure there's many of them, you might have used Verilog, a DSL for doing some hardware stuff. But in the functional programming community, when we talk about DSLs, often what we really mean are something called EDSLs or embedded, too many surprises, embedded DSLs. And so what an embedded DSL is it's a DSL that's embedded in some kind of host language. And there's many of these. For example, Akka is a really famous DSL for doing actor programming in Scala, and you can see here they have these lovely combinators, actor and become, which take some kind of values and turn them into something specific to the domain of programming with actors. Specs2 is also another popular testing framework in Scala. It's a nice DSL, and it has these combinators like must and have size, which are really specific to testing and working with values. For the people in the Haskell community, we have a plethora of DSLs as well. This is a famous one, Haskell, which abstracts over some concurrency and system kind of programming stuff. And all of these EDSLs kind of share a common paradigm. They all start with some value, and then using combinators, they produce something that's sort of like domain specific. So I'll give you a real example. You might have a skeleton, and you might say, this must have a sword, and it must start with flames and end with flames. And you can use these combinators to produce your domain specific value right there. And this is great. I mean, I built that. But the problem is that these embedded DSLs, they're not extensible. So for example, with Akka, which is a great framework for programming against actors, if you wanted to take your actor system and then say like, you know what, we love Lightbend, but we're going all in on Twitter Futures. And you wanted to take your actor system and have it run on Twitter Futures and just reinterpret that whole thing and have it run on a different concurrency substrate, you're out of luck. Similarly with Haskell, if you wanted to not have it run in Haskell's I/O monad or something different, you're out of luck. And these EDSLs are really powerful, they're really useful, they're prevalent across all of the language ecosystem, but they really lack this extensibility, and sometimes we really want this extensibility. So this is where type-level DSLs come in. So a type-level DSL kind of inverts the value combinator meaning paradigm. To compare with a DSL, a type-level DSL starts with some type, and we use typeclass resolution to produce a value in our language. And it uses some of the same machinery. We're just kind of working at a higher meta level. We start with a type, we use constructs in our language to work with those types, and then produce values in our language. And the fact that we can do this, use this type class resolution, will give us this extensibility, and I'll show you kind of how this works. So an example is Haskell servant. So this is if you attended the workshop yesterday, or maybe you suffered my weird demo yesterday, you might be familiar with this. It's like a web framework, basically, where you describe your web API as just a big, giant type. And they have some little combinators to make you construct these obnoxious types, but you describe it as a type, and then you use type class resolution to produce things like a server, maybe a client that talks to it from Haskell, maybe a client that talks to it from JavaScript, maybe a server that produces mock values. So here's an example. This is the Package API, which is the Haskell package manager. And here we have, so it's just a type, and we use these little combinators to bind paths together. So we have a type level list here, and we basically say that if you were to get against /user, you would return a list of user summaries. And you can construct even more paths. Like, for example, here we have, if you get /user, and then you want to capture something in the path, then we're going to return a user detailed. But what's really significant about this is that what we're saying right here is that not only are we going to capture something in the path here, like a username or maybe an ID of a user, we're going to expect that it parses as the type username. So as somebody working and looking, if you're like in a code base and you're like, what is my web API doing? It's my first day on the job. I really got to impress some people. And you're looking like, what are the types that are dealt with here? You can just read this verbatim and say, oh, I'm expecting to get a username and I'm expected to return a user detailed. And in Servant, we interpret this type using type class resolution and produce, like I said, a server that when this request is made will return this. We can also produce a client that will give you functions that you give it a username and you get back a user detailed, as if it was talking to the web server itself. We can even produce a mock server. Suppose you're like, I've had it up to here with Docker Compose, I've had it up to here with scaffolding a whole system, I just want to make sure my program doesn't blow up when it talks to the server. You can create a mock server that, if you have Scala check or quick check in the case of Haskell instances for these types, will return random data back. So in Servant, this has been extremely successful. On top of the three I've listed here, you can generate JavaScript, like JavaScript code to talk to these services, Ruby code to talk to these services, and there's an ever-evolving ecosystem of things that will interpret this type-level DSL and produce values in different domains. And so I really want to convey this and show you how it works, but I think the best way to do it is to build one together, because some of the mechanisms are a bit subtle. And at the end of this, you'll see that what is a really fancy-looking type framework has a very clear kernel, maybe not so simple, but clear and small. What is going to be essentially 20 lines of code. So we're going to build a type-level DSL. It's going to solve a particular problem domain that I had at work, which was this, what I call this heterogeneous event sync. And this is what it's going to look like. So we want our type DSL to solve this problem. So Soundcloud, if you haven't visited it, you should. It's a great website. You can listen to as many lit tracks as you want. And when you do, we're going to end up generating some events. Not because we're some conspiracy trying to spy on you, but because we want to deliver some nice recommendations, of which is part of my role. And as typical of any event-driven architecture, there's often some horrible event sink that's got to consume all these things and turn them into something we can put inside of the data lake. Raise your hand if this is your current architecture at work. But what makes these sort of event syncs kind of problematic is that we don't just shove events down them. Like in our case, we end up wrapping these in some kind of envelope so that we can route them and dispatch them. And so, we might say that some event has the name click or a play or a pause. We're going to be using this click, play, pause throughout the example. And each of them might have a different payload. So, for example, a click might have a page, but a play will have a track. And so you can imagine the kind of code that's in this event sync. I mean, if you were to do like a first pass before you did some refactoring and made it all beautiful, it might just be like, if the click is event, then parse as type event. If the click is play, parse as type play. You know, you'd have this like dispatching where for each name here, we got to parse it as a particular type. And this makes it really challenging to extend. So for example, maybe you've written all this for working with JSON, and now you want to write it all. Now you have to like redo it or do something if you want to start parsing protobufs or Avro or some other custom homebrewed encoding. Maybe you need to get a list of the events we currently consume for some analytics, or maybe you want to start taking the same list and not just routing them in the event sync, but inserting them into some analytics database like Redshift. And so you're constantly working with this canonical list of events, like these are the bespoke events we will consume in this event sync. But you're having to write all this code that's like trying to use it, and you really want to be able to just say, here are the events, and now I'm going to generate all of the code that will consume it and do different operations on it. And so that's what we're going to build together. So the requirements for this event sync are that we must accept events of different types. We're not going to assume they're in some huge class hierarchy, that they're going to come from different places. We need to be able to dispatch on like a string, essentially. And then we need to parse the payload as a different type in each of them. So that's what our goal is going to be to build today. Our type level DSL is going to look like this, and we're going to build it in 3 steps. So the first thing we're going to do is talk about, you know, anytime you have a DSL, you have to have a little bit of syntax to represent these things. You might remember the servant example had all these little weird combinators. So at the heart of this is a way to construct a list of types. And so we are going to show you how you can encode lists of types as embedded tuples. There are lots of encodings. You know, Haskell has a first-class encoding. You can use Shapeless's heterogeneous list as an encoding, but to keep things simple, we're just going to use tuples. Then we're going to create a type class as like a first pass, a simple type class that will crawl this list of events and produce a single value. The value will just be the string, which will be the event names that we bind to each of these. And we're going to use this not because it's a terribly useful thing, but it demonstrates some of the core principles of it. And once we're done that exercise, we're going to write a method that will do the zany dispatching that we discussed earlier. So let's talk about how we encode these lists. This is really at the heart of it, and I want to really make sure that at the very least we're on the same page when we talk about this. So when we think about a list of types and how we might encode them, we need 2 things. One, as any list, you need a nil element. So we're going to just use unit, for example. In Scala, in Haskell, it'll be slightly different. But we just need some type that represents you've reached the end of the list, just the same way you would model a linked list at the value level. And then we need like a cons operator, which would be you have a head and then you have a tail of the list, and we're just going to use a tuple for that. So each tuple here will have an element. This would be the head, and this tuple would be the tail. This would be the head, and then this tuple, which is the end of the list, would be the tail. So you can take this kind of list of int, string, and char and model it as a list of embedded tuples. So I want to let this marinate in your minds a little bit. You know, if anybody's confused, I know it's super intimidating to ask a question, especially when the slides keep disappearing. But if you have a question about this, let me know, and I'll just take a moment to look at the glory of this skeleton GIF while you ask. Okay, so we're going to be using this encoding throughout. So let's begin. I've put the code right here. So if you have your laptop out, I'll just give a second. You can go to goo.gul/em6kph. Not like you'll remember that. I did actually try to spend 3 seconds to figure out how I could get a short URL with meaning, and then internet in Cadiz is beautiful as it is. Okay, so I'm gonna be on a console for this, so it's gonna get a little wild. All right, so let's just see if we can get a little bit better lighting here. Oops, not that one, dark. Is that better? Yeah. Yeah, okay. So, some preliminary stuff that we need to build. we have our events. So as I was saying, click, play, pause. This is what's coming through our pipeline. They're going to be simple case classes, just some dummy data enough to make each one a little bit different. This is obviously not how you would model them in real life, but they will make our lives a little bit easier. We need this end of the list, this nil for our type level list that we just call literally end of the list. And here is our DSL. It is the list of events. So now we need to start doing this thing where we take this list of events, we take a type class, and we crawl it to produce a value in our domain. So let's do that. As I mentioned, the first thing we're going to cover is we're going to generate a string that just has the name of the events. At the heart of all of these type level DSLs, you have your type, and the way you interpret them is using a type class. So the type class that is going to interpret them is just going to be called named, and it will have, let's see if we can get a little bit bigger here. And it will have a single value name as a string. And this type parameter is where our type level list is going to appear. So we'll first create some instances for our events. So you can imagine the click will just have the name click, and the play will just have the name play, and the pause will just have the name pause. Hopefully this is straightforward. And now we're going to sort of start shifting the gears of abstraction a little bit. So anytime you're doing induction, say you're processing a list, or you're doing a programming exercise, or God, heaven forbid you're on the whiteboard in some job interview, and you've got some recursive data structure, generally a good practice when you're faced with recursion is to start with the base case. Rather than looking at the recursive states, start with like the bottom of the tree, what do I do in this instance, and then we'll tackle the more complicated one next. So we have our type level list. It's a bunch of embedded tuples. We have a type class called named, and we're going to use that type class to crawl this type level list. And our base case is going to be creating an implicit instance for the end of the list. And since we don't really know anything, we're just going to do the most naive thing, which is return the empty list. Okay? So our base case is returning the empty list. As our type class crawls this list, it gets to the end, and it produces an instance that just has an empty string. So now we're going to jump to our induction step. So in the induction step, we want to produce an instance of named where E is our head of our list and tail is the tail of our list. This is the goal. And we're going to assume, like you do in recursion, that we have an instance for the tail. So we know all the names of the tail, and we're going to assume that we know how to name the head. And then we're just going to create this string where we just concatenate these things. So we take the instance of named for our head, and we put it into a string here and have a little comma, and then take the name of the tails and put it in the string there. So if we go and run this code here, Scala, please work. Okay, good. It's like having to compile it and run it. I don't know. Anyways, I promise you the performance is not that bad. So just to recall, here is our type level list as these embedded tuples. And then if I create this little helper method, I skipped over that real quickly. If I have this little helper method right here that just pulls the implicit out, so I can call it with E, it'll look for the implicit and then produce the name. If I do that right here with events as represented here, I'm going to get click, play, pause. Now, I'm going to do something bold. I'm going to change code. And if I then just remove one of these events, so let's just remove a type here. Okay. And then I'm just to make the printing a little bit more clear. Oh my. I'm going to remove it from here as well. And we're going to hit save. We're going to go over here and run it again. We should see that we're now we represented a new list, and at compile time, when it compiles it, it's going to produce a new value. So you should see now we only get click and play because we only have click and play as events. So I'm going to undo all my changes before the presentation turns into a disaster, and then we're going to go and look about what's happening. So to kind of explain what's going on, we started with this base case. So we looked for an implicit named of end of list. This was, do we have a name for our end of our list? And we produced a oh, this is incorrect. Anyways, we produced a value where we just gave it the empty string. So if you remember this here, I updated the slides to make it a little bit more simple, and I missed that. But if you remember here, this was our base case right here. And then in our induction step, the following happens. So we call this method, get named events. And so Scala, as it's compiling, says, I need to find an instance of named click, play, pause, end of list. And it looks, do I have this instance? Of course it doesn't have this instance. But it knows that there's an implicit method that if you know the name of this click and an instance for this tail, it'll produce an instance. So then it says, okay, I have a named click. I know how to name clicks, but I don't know how to generate a tail. So then it starts looking for the tail. Okay, so do I have an instance for this tail? No, I don't. But I do know how to name a play, and I have this implicit method that says if you know how to name a play and you know how to name the tail, we're going to try to find an instance there. So then it says, do I have an instance for this tail? No. So it says, okay, I'm going to look for one. And it says, okay, I know how to find a named pause, and I know how to find a named end of list because that was our base case. And then all of this resolves, and the Scala compiler can produce at compile time the instance that you're looking for, which is exactly what happens when you compile it. So now that we've shown this simple method of just taking this type level list and generate a value and kind of having an intuition of how this works, we're going to sort of shift the gears of abstraction a little further. We're going to now try to do the dynamic dispatch that we discussed at the beginning. So, as always, anytime you're working with the type level DSL, you have your type level list, and you need a type class to do induction on that list and produce a value at compile time. So the type class we're going to use for this dispatching on the event names is going to be called handle events. And it's going to have a method called handle event that takes a string, which is going to be the event name, like click, play, pause, and it's going to take the payload, which is the thing we're going to try to parse as a click, a play, or a pause. And then it's going to produce either there was a success, you either found the event, or either there was failure, you did not find the event, or you did not parse it, or it's going to produce out. And so you might ask, what is this out? This is an abstract type. And so I go to you and I say, if you have this list of events, click, play, pause, what is the output of our event sync after a successful parsing? You either have failure, or you have a click, or you have a play, or you have a pause. But our type level DSL has to work for any list of types. So if I have the list click, play, pause, page view, timestamp, whatever events, the output of this parsing has to be this generated type, which is either failure or click or play or pause or page view or timestamp or whatever. And so what we need to do is generate the output type while we're recursing over the list. And this is really fundamentally amazing that you can do this. So we can generate these types dynamically as our compiler is working through them. So let's go through. As we did with the previous case, we're going to do the same thing. We're going to start with the inductions, with the base step, which is the bottom of our type level list. In the base case, which is creating an implicit instance of handle events for our end of list, basically the idea here is that you've reached the end of the list. You've searched through all the events, and you haven't found the event you're looking for. So at this point, you've received an event that you don't know how to work with. The only thing you can do is return an error. So the output is nothing, which communicates you can't actually return anything. You must return a left, which is an error. And if you look above here, this makes sense because the type of return here is either a string or out, and here we return a left. So the next part is we need to do our induction step. So we've got the base case right here. We now need to find an implicit instance of handle events for the induction step, which is for an E and a tail. And to do this, we actually need to make some assumptions about E. So the first thing we need to know, can we actually even parse this thing? So we're going to use another type class to put a constraint on E that will say, can we parse it? We're going to use this really simple parser. It's just a from string type class. It has a single type parameter, a method from string that returns an option. So this is to say that any type here, E, can be transformed from a string to either failure or an instance of it. And we provide some lists, some instances for our types. So, here we're parsing a click, we split on the string. This is like the worst programming ever. We split on the string, we to-list it, we match, and then we just return it. And then if we don't get a user in a track, we return none. We just assume that it's like a tab delimited list here. And there's a bunch of other instances for play and for pause, and we're looking at numbers, and there's all this boring stuff here. But now that we have this from string type class for our events, we can do the induction step. So remember, we're trying to generate code that accepts an event, looks at the name of the event coming in, and the name of the event in our type level list, and says, do they match? If they do, I'm going to try to parse it. If not, we're going to go further down. So when we're in the case of an E and a tail, we make the following assumptions. We assume that our event at the head can be named. So we can extract the name and try to match it with what comes in. We assume that it can be converted from a string so that we can take the payload and try to parse it. And because this is induction, or because we're recursing over this list, we assume that there's an instance of the tail for handle events. That is, we know how to handle events for whatever appears here, which is going to be more tuples or the end of the list. So we're now ready to represent the out. So if you're somewhere in your list and you're trying to understand what am I going to return, basically you have two options. Either the event matches, and then you can return a value, so you will return E, or you'll go further and return whatever comes down in the tail instance. So this is this sort of at compile time generated type here. So we're using the path type right here from the tail instance of handle events. And this is really, again, another super powerful thing in the Scala type system that you can do this. This is a value, and you can extract from it a type and generate a type at compile time. And our actual event handling logic is, what you might do on a first pass. You just grab, so we have an event name and a payload coming in, we match. Okay, is the event name the same as the named event from the type class here? So we got a click, is it a click? We got a play, is it a click? Is it a play? Whatever. If they do match, then we'd use the from string instance to parse the payload. Okay, so they match. Now we're going to take the payload, we're going to parse it. And if it succeeds, then we wrap the whole thing. We have to return either string or out. So it was a successful event, and we parsed it correctly, so we return E. Otherwise, we just return left with a string. If it's not the same event, so if we got a play, but we're looking at the click instance, then we simply use the tail instance of handle events and call handle event on that. So we're going to say, okay, we couldn't find anything right here. The code path we're at is click. You wanted a pause. We're not a pause. We're going to pass it down to the tail. We pass the event name and the payload, and we say, what did you get back? Okay, you failed, so we're going to propagate that fail upwards, or you succeeded. You found an event, but we need to say that for where we are in the code path, we didn't return a click. We returned a different event, which is the left-hand side of this either. So that's why we have to wrap this right in the left. Whew. So this kind of thing, again, my purpose of the talk is to inspire you. I mean, if you walked out of here understanding every line of code in this, then you are a magician and a wizard. It took me probably 10 years in isolation of thinking super deep about this subject, conjuring miles in my mind to understand this stuff. But hopefully you can refer to this code and be inspired, because if I show you what it's doing in the console, it becomes slightly clearer. So for example, I created this helper method that just tries to grab that takes a list of events and just tries to grab the implicit from there and then calls it. So we're going to use that helper method to call some code. And if we call it here, you're going to see, might be hopefully what you expect. So I'll try to just get this a little bit bigger. So we have our type level list, right? Click, play, pause, end of list. And then here we're going to try to handle events. So this is the method we're going to call. We're going to pass it the click. So we're saying, we're going to give you a click. I want you to try to parse a click. And what we get back is write, click. Okay? So this is sort of what we might expect. It's the first, we had a successful parse, and it was the first element. If we tried to do the same thing on a play, so we give it a play, and then we also encode a play, we get that it was a successful parse, but it wasn't the first element. That's why there's a left here. It was the next element, which is a play. If we try to do this on the pause, then it'll do something sort of similar. We have a successful parse, but we have to go 2 layers deep to get to the pause. And remember, all of this is generated at compile time. So we have like one single instance with a bunch of nested methods that do all this resolution. If we try to give it a wrong payload, so if we give it just something that's not a number for a play, we just get the error. And if we try to dispatch on the wrong event, we also just get the error. And if I do the same change I did before, where I remove one of these plays and then recompile and run it again, you're going to see, so if I remove pause, you're going to see that where we had a wrong event here, we'll have a wrong event here. And remember, all I'm changing is the type. I'm not changing any values or any logic, only the type. So let's go and quickly do this. We'll remove pause here and then do that to make it more clear just from the string so you know what you're looking at. Save and go. So this is our new list. This is our pause. It didn't find an event. It didn't find this event anymore in the list. We didn't change any values. This is all represented as the type. How am I doing for time?
10 minutes.
I got 10 minutes. Okay, so just to give you a little taste, a little inspiration, because I promised you some Haskell, I want to also show you what this looks like in Haskell. And it's shockingly almost identical. So again, we start with this preliminary definitions, click, play, pause. We provide an uninhabited type for end of list. Rather than using unit in Haskell, we just make an uninhabited type. And here's our list of events. It's the same syntax as Scala right here. To take that list of events, interpret it using typeclass resolution, and produce the string, as we did in Scala, in Haskell, it's the same thing. We start with a type class. The only difference is that instead of just having a name that is a string, we have to pass this proxy. And this proxy is different because in Scala you have these objects and the compiler can reference them and hold them, but in Haskell we rely on the Hindley-Milner type inference, which requires that we have a type here so that we can do the inference correctly. Aside from these proxies that are littered throughout the code is honestly identical. So we create some named instances for our events, click, play, pause. We create a name instance for our base case, and we produce an induction step where we assume that we have a named E and a named tail. We produce a named E tail, and we do the same thing. We pass a proxy here, we have a comma, we pass another proxy there. And it will produce the same code. For doing the dynamic dispatch, here's our type out again. We have a type class that will crawl this type level list, produce a new type that represents all the different cases, a coproduct if you will, and it's identical to what we had in the Scala example. Our handle event method takes a proxy, 2 strings for the event name, the payload, and will either fail or produce the output. The base case for this is, again, it's identical. We for the out type, we use what's equivalent to nothing, some uninhabited type. And when we're handling the event in the base case, we just return left. So we just error out. We need a type class for parsing. Here's a type class for from string, which just takes a string and turns it into a maybe A, the Haskell equivalent to option. And here are our instances after some horrible code for click, play, and pause. And now we're ready for our induction step, which will produce this out for e-tail will be either left, you recurse further, or e, you return the type you got, and then handle event here will take the proxy, which we ignore, the event name and the payload. We have some statements in here, and we do the same thing. If the event matches, we try to parse it. If it's successful, we return this embedded right. If it's not successful, we return left. Otherwise, we run, why is this happening? We run handle event, and then wrap it back into left. And if you run the code in Haskell as we do in Scala, you will see that it is the same. So here you go, you get this right click, right, left, play, right, left, right, pause. And you get the same errors. So they are identical encodings. So we've recreated dynamic dispatch, but we've done it statically. And I think that this is a huge accomplishment in our code. And to recap, we had these named instances, and we use this name method here. We had the second interpreter. And so you might ask, we were able to take a type level list and produce a value by interpreting it using a type class, and we were able to interpret it using a different type class and produce a method that will do the dynamic dispatch. And we could just keep doing that all day long. I want a thing that will interpret that list, and instead of assuming it's parsable, assuming I can insert it into a SQL statement and then produce a dispatchable insert command based on those events. You could just do this all day long. And in Haskell, in Servant, they've done this all day long. And so you might ask, can we have it all? Can I stick my record player and my tape deck inside my player? And the answer is that, almost. You can almost have it all. And some of the problems that you encounter when you do this is that compiler messages can be a little frustrating. So suppose I had my type level list, click, play, pause, and instead I just inserted an int in there, but I didn't change any other code. So what you're going to do when you try to use handle event is that it's not going to be able to find a from string instance for int, which is good. This is the compiler error you want, right? Okay, I know what's going on here. I got to fix this. I got to write a from string instance for int, and then boom, all my code will compile, and all the things will get generated at compile time. But if you do this in Scala, you get, unfortunately, I can't find the implicit. The compiler just gives up. So you can imagine in our case, we had click, play, pause. There's 3 things. You get a compiler error like this, you just check 3 things. If you have 30 events and 3 different type classes for each one, this is a horrible compiler error. Miles has assured me that we can fix this, and I believe in him, so we can get through this. You might also say, well, why do we have these proxies around? What if I just remove the proxies? Certainly I should get some kind of sensible error message that, a human can understand. And I could not, for the life of me, understand. I'm pretty good at understanding the zaniness that's happening in the Haskell compiler, but why is it saying that my events 0 is not events when very clearly this is events, this is events? What is the problem here? Events equals events, come on. But the problem is there's some weird subtlety with the class constraints here, blah, 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 blah. But the point is, I encountered this error when I was preparing the talk. I didn't put proxy in there. I was like, it's just going to be the same as Scala. I'm a wizard. And then I was like, what is happening? Oh my God. And it was because of this. And it took me a while to remember this little trick. So there are some things that really make you throw your bonehead, really frustrate you. And this brings us to this dialectical portion of the talk. So, we started with DSLs, and we realized that DSLs are great and wonderful, but they don't have this extensibility. And that led us to produce these type-level DSLs, which is kind of like a way of having a DSL, but having this infinite extensibility of having it all. But what we found was we saved so many time on runtime bugs, but now we're hunting down these corners of the compiler, these bad error messages on all this, and you produce this sudden appreciation. You're like, wow, values. Values are so good. I can hold a value. I can bring whatever semantics I want. And so it's sort of interesting that at the end of this, I was like, I love using these type level DSLs. They're amazing and they're super powerful, but you sort of have this nagging adoration for the value and how simple it is. So to recap kind of what we did, we showed you that a type level DSL can use type class resolution to crawl a type level list and generate values. And this is the central mechanism. It's the mechanism used in Servant. It's the mechanism that is used not necessarily for type level DSLs, but if you look in the Shapeless code base in Scala, you'll see this induction over lists everywhere, and you can use this code as your reference example if you're trying to understand that. We showed that type level DSLs are extensible. We had one single type, but we never changed it, except to show you some different errors, but we never changed it, and we produced a string value and a method value, and with a little bit of imagination, you can produce all kinds of different things. We showed that they only use core language constructs. All of this happened at compile time, but none of it used macros. And we only used tuples and either. We didn't use any extensions. Everything was encoded in the language using core constructs. Not only this, but the constructs are available in both Scala and Haskell. So this is somewhat like of a universal thing. If I can do the same thing in Scala and I can do it in Haskell, maybe there's some sensibility to these type level DSLs. And you can see them in the wild. As I mentioned, Servant is a great example. Check out all of the different things people are building into that ecosystem. And Shapeless, if you want to see some really great usage of induction over these type level lists. But the compiler errors can be unforgiving. And until we have a language like Idris, type level DSLs are our only hope. So I thank you for coming, and I want you to go forth and write some DSLs.